All right, so good afternoon, everybody, or good morning, or good night, good evening, whenever you're watching this. This is Math 0310, and first of all, I want to talk about a schedule for the rest of the semester and a couple of other announcements that you will probably be interested in as we go into the third exam and the final. So today is 11/16, and so today we are going to do an intro to functions. So this is section 3.5 in your textbook, and this is an intro to the idea of a function. So this is a big deal going into college algebra. I do want to point out that this is the intermediate algebra text. So when I assign textbook homework, I am assigning this out of the intermediate algebra book, not the book that we have been using most of the semester. Whoops, not test, but text. And remember, you can download that book for free just because it's an OpenStax book, and so it's certainly not a book you need to pay for or anything like that. It doesn't affect how you do WebAssign. The WebAssign homework just keeps on going like it's been going. So no questions, no differences there at all. All right, then next Tuesday. And that's the 21st. And yes, we do have class. Lone Star College is open Monday and Tuesday of next week. So yes, I am going to have a lecture or lecture that day. And we're going to look at section 3.6, and we're going to look at graphs of functions in that section, and a couple of other things about functions also. But we're going to look at graphs of functions there. Then next Thursday is a week from today, and so that's the 23rd, and so that's Thanksgiving. Yay. And so Thanksgiving, holiday, and obviously no lecture nothing going on Thursday or Wednesday of next week. I won't be online at all next Wednesday, Thursday, Friday, or Saturday. I will have office hours on Sunday for that week, just like always. By the way, so the Sunday of Thanksgiving weekend, I will be definitely will be online. All right, and then the following week, so Tuesday, and that's the 28th of November. We're going to look at sections 2.6 and 2.7, and those are on absolute value. We're going to finish. That's what we're going to finish with is absolute value in section 2.7. And then on the 29th and the 30th, I will be on campus those 2 days. And we will talk a little bit about later in the next couple of days, not today, but we will talk about when I'm going to be on campus and when would be convenient times for you guys to come by and talk to me face-to-face if you have any questions face-to-face. Sandra, do you have a question? And Sandra asked about emailing over Thanksgiving, and absolutely. I'll be checking email over Thanksgiving weekend every day, probably I'm sure a couple times a day for most of the days during that week, during that weekend. And so if you have questions over the Thanksgiving weekend, you can always email me, or you can send me a message through WebAssign. Yeah, either way, and I will definitely respond to those over the weekend. So yeah, you don't have to wait till Sunday. If you have questions, absolutely, you can talk to me then. No question about that. And then 11:30, that's a Thursday, November the 30th, exam 3 window opens that day. And then I want to point out, let's see, a couple things here actually. So let's see, that goes through December the 5th for that testing window. And then the final exam is going to open a week later, just a week later there. So 12/7, the final exam window opens. So the final exam is going to come right after exam 3 pretty much. And we're going to get started with that. So probably my lecture on November 28th, the absolute value, that's going to be my last live lecture. I may be online possibly once for you guys in between there, for just for you to ask questions, but not really a formal lecture there at all. So I kind of wanted to point out the rest of your schedule for the year. I want you to pay attention to your WebAssign homework. And I know I say this every lecture, so I do want to keep on reminding you. I can't help it. I'm a dad, so I'm going to nag you about it and keep after you to get your WebAssign homework done. The next due date, I believe, is November the 27th, and so you've got a little bit of time, but don't put that off. Also, a couple of other announcements. Remember, the Exam 3 review is up. And so go to my Google site and go look at the Exam 3 review. The final exam review I'll say is going to be up by Thanksgiving. It's a departmental final exam review, and so I'll just get a copy of it and I'll post it on my Google site so that you can start looking at what's going to be on the final exam. Finally, the last thing, I think, and you guys are my survivors, all of you who are watching this live, and also those of you who are going to watch the recorded version later. So you're my survivors. I am going to allow scientific calculator usage on both Exam 3 and the final.
Wait, so we can use a calculator on the last two?
A scientific calculator.
Okay, yay.
And yeah, I knew that would make some of you happy. So,
yes, thank you.
What I do want you to, one thing I want you to get into, so many math students are in this mindset, and some of you kind of tended in this direction also, that you've convinced yourself otherwise now, but a lot of you are in the mindset, I can't pass a math class unless I have a calculator. I can't pass a math class unless I have a calculator. And that's not a good mindset to get into at the beginning of a math class. When you start a math class, you need to be in the mindset, okay, I'm going to work hard, I'm going to do the best I can, I'm a smart person, I can do this, right? And so I don't ever want you to have that mindset, not just in a math class, but just in general at the beginning, to say, I can't do this unless blah, 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 whatever it is. So I don't want you to be in that mindset. You're going to be a stronger college student the rest of your college career if you always go into any class with the mindset, I'm going to do my best in this class and I'm going to pass this class. I'm going to do the things I need to do to satisfy the instructor's requirements for this class, and I'm going to pass this class, right? And so I don't want you to get into that mindset that you can't pass it unless something is there to help you in some way. So I just don't want you to think along those lines. So anyway, I wanted to point that out. And then finally, the last thing before we get started is the spring schedule. And I do want to remind you to register, if you're going to take college algebra in the spring, to register for college algebra. And all of you who are with me live today, or again, who are watching the recorded version, you're all my survivors. I'd love to have you sign up for my college algebra in the spring. I have 2 online sections. I've had multiple people ask me over the last week or two, because there's 2 sections of college algebra that I'm teaching. It doesn't matter which one of those 2 you register for. Either one of those is going to be fine. So you just register for one of those. So, Sandra, do you have a question, or that was just a comment? Okay. All right. So I guess just a comment there. But so sign up for college algebra, whether you're going to take it online or face to face, and you have to make your decisions and what you're going to do. But I do encourage you, if you like this format, if you think you can survive this format, you can do this in college algebra. And if you can survive this in intermediate algebra, you can survive this in college algebra also. Sandra said that she tried to sign up through the day yesterday and was not able to. I am not sure, Sandra, why that would be true. You may need to, if you can't do this online, and this would be true for everybody, if you can't do this online, then you need to call the registrar or go into campus to see why you can't get in. I can also probably facilitate you registering through the counselor that we have in the Math Science Division. If you are having trouble registering for the class, then just email me that you want to register for one of my sections, and I will send the counselor your ID number and your name and say register this student for one of these 2 classes, and then you'll have however long to pay for it. So if that will help any of you, I absolutely don't have a problem doing that at all. So just let me know that, okay? Any other questions about the spring schedule?
Do we know what time it's going to be?
Oh, thank you, Charlotte, for asking that question. In college algebra, is going to be really the same time this class is, except Monday, Wednesday. So it's going to be 9 to 10:15 in the morning on Mondays and Wednesdays when I'm going to live lecture in that class. So my sections, let me write that down here on the screen too. My sections for 13-14 will be 9 to 10:15 a.m. Monday, Wednesday for live lecture. Okay, so again, just like this semester, if you can't attend live lecture, you can always watch the recorded version. But I wanted everybody to know going into registration when that time period was. And so there is a comment line in the schedule. So it should come up in the schedule that that's what I'm doing, is I'm live lecturing at that time period. So I would be interested in seeing if that's your experience, if that comes up, because that's what's supposed to happen. So. All right, so if there's no other questions about the spring schedule, then let's get started. Today, last time we talked about linear inequalities and 2 variables, so we have finished up our discussion on lines. That's the last thing we're going to do with lines. And so we are now finished with lines. So I'm going to say we are now finished with linear equations and inequalities in 2 variables, right? I.e. lines, right? We were talking about everything you ever wanted to know about lines. And so that's what we have finished up now. And so now the next topic we're going to spend the next 2 days on, we want to talk about functions and the idea of a function. And I am going to ask you guys some questions, and I'm going to want you to participate with this for the rest of this lecture for sure, as we start talking about what a function is. And so what I'm going to do is I am going to write down the definition for a function that I use, and I'm going to warn you that this definition is a long definition, and if you read through it, it might seem kind of confusing when you read through it, exactly what it means. And so what we're going to do is we're going to write it down, and then we're going to pick it apart, and we are going to look at examples, and we're going to make sure that you understand what that definition really means and how we use it as algebra students to our advantage. Okay, so I'm going to jump right into this, and I'm going to write down the definition right away. So a function is a correspondence between 2 sets called the domain and range. And by the way, because you got 2 sets there, this is why we had to wait until we started talking about equations and 2 variables before we could talk about functions, because it's a correspondence between 2 sets. You have to have 2 variables when you're talking about functions. You can't talk about functions if you have just 1 variable. Okay, function is a way of relating 2 sets to each other. And the 2 sets are called the domain and range. And so you have this correspondence between the domain and range. in which each, and that's an important word, element of the domain is made to correspond to exactly one element in the range. Right, and I can understand. I can just see you. If I can't see any of you, but if I could see you, I could see some of you with your eyes rolling up in the back of your head, going, "Oh my gosh, I'm not sure I understand anything about what that means," because it's just a bunch of words, and I definitely understand that. So you've got two sets. You've got the domain and the range. Now these sets, notice it doesn't say that the sets have to be numbers. It doesn't say they have to be, letters, anything like that. It just says two sets of things, of objects. And you have a correspondence. You have a way of taking these two sets and relating them to each other. You have to have a rule that tells you how to relate the two sets to each other. And that rule is what is either a function and satisfies the definition for a function, or it does not satisfy the definition for a function. If it doesn't satisfy the definition for a function, then that rule is simply called a relationship, or short for that is a relation. So any way of pairing up the two sets and connecting the elements between two sets is a relation. It's a relationship between the two sets. But only certain of those relationships, only certain of those rules actually satisfy the definition for the function. And in order for the relationship to satisfy the definition for the function, two things have to be true. Each element of the domain has to be assigned to something, and so you can't have a domain element that doesn't get assigned to something by the rule you've got. And every domain element can only be assigned to one range element. It cannot be assigned to more than one. So that's when I use the words exactly one. So now notice I left a little space underneath this definition on this page because I'm going to come back and write a couple of things down there in a minute. But what we're going to do is we're going to flip the screen and we're going to look at an example or two and talk about some things and see if we can analyze whether they're functions or not. Okay? And so we're going to look at some examples here. And then we're going to come back and write some things on that page. So examples, and the question basically is function or not a function. All right, so we're going to start off. You have to start off with a domain and a range. And so the domain is going to be the set of people in our class. All right, so the domain, and a lot of times we use the capital letter D for domain. You put a set braces here, and then I would just write down the people that are here with me today. So Anne-Marie and Charlotte. I'm not going to write everybody's names down, but I'm just writing them down in alphabetical order. Right, so Anne-Marie, Charlotte, Janessa, Jose, Justin, Sandra, that's my domain. Right? And then all the other people who are going to watch this later who are in our class. So there's our domain, right? Just a set of people in the room. And the range is going to be the set of makes of car. Okay? So set of makes of car. And so that's our range. We'll put a capital R for that. And can you tell me what would be things that would end up in that range?
Ford.
Okay, there you go. That's a good one. Keep on going.
Honda.
Tesla.
Okay, I've never had anybody say Tesla before, but there you go. Believe me, I've been using this example for 20 years to introduce functions. And certainly 20 years ago, Tesla wasn't to make at all, but never had anybody say Tesla. So we might as well go for broke here. Give me one more. Somebody give me one more.
Dodge.
Dodge. Right, and this would go on, right? We have a relatively lengthy list of makes of car, but we could write them all down. And so that's our range. All right, now, if I give you a domain and a range, I don't have enough information to talk about whether I have a function or not. Because what I need here is I need a way of relating domain elements to range elements. I need a rule that tells me how to assign domain elements to range elements. So we need a rule that tells us how to assign domains to ranges. All right, so how do we take a domain element and assign it to a range element? Okay, so so what we're going to do is we're going to talk about several rules here, and we're going to look at whether these rules satisfy the definition for a function. So rule 1, this is going to tell us how to make the assignment. Everyone is assigned the make of car in which they were driving the last time you were on campus. And whatever campus in the Lone Star system is fine. Right now, if I was teaching a face-to-face class, I'd be doing the same thing by telling everybody everyone is assigned the make of car that they arrived on campus this morning in. But you guys may not have actually been to campus this morning. Probably most of you weren't. And so just the last time you were on a Lone Star College campus, what make of car were you driving? And you didn't even have to be driving. You just had to be in the car. So, all right. So, Anne-Marie, answer that question.
I drive an Acura.
Okay, so we would put Anne-Marie here, and the way we would show this relationship is we'd put the domain element first, and we would make an ordered pair out of it. And we would put the range element that domain element got assigned to, and we put that second. And so we would have an ordered pair here that would be Anne-Marie and Acura. Charlotte.
A Honda.
And Janessa.
I got a Dodge Dart.
We don't care that it was a Dart, by the way. Just
yeah,
care,
Dodge.
just care that it was a Dodge. That's all. That's right. That's okay. And let's see. And Jose and Justin and Sandra. Some of you are online, but let's see. Jose said Nissan. And what about Justin and Sandra? Do I hear from either one of you? So Sandra says that she would rather have. Now, Sandra said Honda, but then she said she'll take GMC. Now, I don't want you to do that. I want you to put the car that you arrived in. So I'm going to say Honda here. And there's a reason why, by the way, that I wanted to put Honda there. And Justin very quietly said something in there. What did you say, Justin?
I drive a Honda.
Honda, okay. So we have lots of Hondas there. Let's see, so Justin and Honda. Right, and if we took all the people that were watching this video later, we would write their ordered pairs down also. So we have this big list of ordered pairs. And so the question is, does this satisfy the definition for a function? So two things have to be true for it to satisfy the definition. So does this rule satisfy the definition for a function? Now, don't forget that rule, let's go back and look at the rule for a minute. That rule said two things had to be true in order for a relationship between two sets to be a function. Every element in the domain has to be assigned to something. So that's the first thing. Well, kind of the way I wrote this, unless you've never been onto a Lone Star College campus, right, you've been assigned to something here. And so based on the way I wrote the rule. So we're going to assume that everyone gets assigned to something, right? So that's not an issue here. Everyone does get assigned to something. So each element in domain is assigned. And we're just going to say, yes, that's true, just because of the way I wrote the rule right there. All right. So that's the first requirement's true. Then the second one is this exactly one part. And this is the one that kind of catches people sometimes a little bit as far as getting confused on that, for sure. And so what's probably worrying some of you is that, like right now, I've got all these Hondas there. Charlotte is Honda, Sandra's Honda, Justin's Honda. And so you got all these different people assigned to Honda. But I want you to look at what the definition says. It says, does every domain element get assigned to exactly one range element? Now, so a way to ask that for our rule is, did anybody arrive on campus, the last time they arrived on campus, did they actually arrive in two cars? So, precariously balanced, where you had 1 foot in one car, 1 foot in the other car, and the two cars are kind of driving right next to each other. And that's how you arrived on campus, is in two cars. Probably not. Probably all of you arrived in just one car, right? And and so that, how many cars did you get assigned to? How many makes of car did you get assigned to? All of you got assigned to just one make. Nobody got assigned to two makes of car. Probably nobody arrived in two cars at the same time. So everyone is assigned to exactly one car, or one make. Everyone is assigned only one make. They arrived in one car only. Arrived in one car only. See, it doesn't say, the definition doesn't say that everybody had to be assigned to a different range element. It just says everybody has to be assigned to one range element. And so this what's going on in our problem here, that some of you, multiple ones of you, got assigned to the same range element, it doesn't matter. As long as you got assigned to one, that's all that matters. So Charlotte gets assigned to Honda. She got assigned to one. It happened to be the same one that Sandra got assigned to. That doesn't matter at all. Both of you just got assigned to one range element. And so this satisfies the definition for a function. That gets checked off also. And so this relationship is a function. This relationship is a function. Okay, so this satisfies both of those requirements. Everything gets assigned to something. Every domain element gets assigned to something. Every domain element gets assigned to just one thing. And so it definitely satisfies the definition for a function. So a couple of things here. Notice that in my list of ordered pairs, there were some y values that got repeated, right? Because we had multiple people being assigned to Honda. And there's probably others that got repeated also if we looked at everybody who's in my class. And so what this means is, went the wrong direction there. What this means is, for this definition, and where I'm going to write something underneath here, is that repeated y values are okay on this definition. It is okay when you have a set of ordered pairs to have repeated y values between two ordered pairs. Not a big deal. That does not violate the definition for a function. And so I wanted to point that out, definitely. The other thing to point out is that most of the time in algebra, when we deal with a function, we usually name it, and we usually name it with a letter. So, like if we took rule 1, the one we just stated, and we might name it F, right? F, G, and H are the most common letters to use. You can use any letter in the alphabet. Typically, you don't use X and Y because we use X and Y to represent domains and ranges. But other than that, we usually, and we don't use the letter I typically because we use the letter I for the imaginary number. So, unless it's spoken for some reason like that, we can typically use any letter we want for a function. And so if we name the rule, in this case rule 1, we name it f, then we can talk about f of x. And what that f of x, this is what's called function notation. And what this f of x means is, what does our rule, which is f, what does it do with the domain value x? So for example, we had Anne Marie a minute ago said that she was assigned to Acura. So we would say f of Anne Marie, our rule, his name is f. F, that rule takes Anne Marie and it assigns her to Acura, like that, right? And F takes Charlotte and assigns her to Honda. And let's see, I wanted to get, who else was Honda? Sandra was Honda. So F of Sandra is also Honda right there. So notice you can get the same answer. As long as you get just one answer, then it does satisfy the definition for a function. So that letter F, when we're talking about a function, is the name for the function. And then what goes inside, in general, what goes inside the parentheses when you're writing this function notation? What's the domain value? So it might be x if x is representing the domain, but whatever the domain is, that goes inside those parentheses. And then the answer to this is the range value, like this. So a lot of times you'll see it written like this, that f of x is equal to y, right? Because x, we're going to use x to represent domain values. We're going to use y to represent range values. And f is simply the name for the function, and it's saying, and the function, remember, is a rule, so it's the name of the rule, and it's saying, what does this rule do with this domain value, right? And it takes it to that range value. All right, so there's our first rule. So let's move on to rule 2. So rule 2 is, and please shout out if you have a question as we're going through this. So rule 2 is the same domain and range, first of all. So we keep, everybody in the room is the domain, everybody in our class is the domain, and the range is going to be the set of makes of car. So rule 2 goes like this. Everyone is assigned to the make of car they own. All right, so everyone is assigned to the make of car they own. So first of all, car ownership. Car ownership is, we have to talk about car ownership a little bit. So some of you, maybe who are watching this live, some of you who are going to watch it recorded later, may have a car that you refer to as your car. You say, hey, that's my car. I'm going to take my car to the movies. I'm going to take my car to the store. I'm going to take my car to school. But it isn't your car, because the car ownership is defined in the state of Texas, certainly, as your name is on the title of that vehicle. Your name has to be in the title of that vehicle. Now, there can be a lien holder on that title also, but if your name ain't on the title, you ain't the owner of that car. So some of you, whether you're watching live or you're going to watch this recorded later, may have a car that you referred to as your car, and it's not your car, right? So let's say we have a student. I'm not going to pick on anybody who's live here right now, but let's say we have a student named Bob who does not own a car. Right? So what happens? Bob does not get assigned to anything by this rule, right? The rule 2 does not assign Bob to anything. All right, now, so what do we do? Rule 2 does not assign Bob to a range. So what do we do? Do we just say that rule 2 is not a function? Do we stop at that point? Or do we do something different? And we do something different here. When we have a domain value that does not get assigned to a range value based on the rule that we're using, we actually take that domain value and we actually kick it out of the domain. So what we do here is we throw Bob out, right? We throw Bob out of the domain. I'll just put of domain there in parentheses. Right? Any domain value that does not get assigned to a range value, we kick it out of the domain. And this is true for any function that we talk about in algebra. If you have a domain value that's not assigned to something, it is thrown out of the domain automatically. So a problem, you may look at this rule as something that's not as mathematical as some of the ones we're going to look at later, but it's just as mathematical as anything else. We do exactly the same thing anytime we see a domain that's not assigned to a range. Now, I'm going to flip to the next screen. I'm going to come back to this screen in a minute, but we're going to come back. But let me flip to a clean screen here. All right. So, for example, let's say that we have a more traditional rule. Let's say that we have our rule f takes x and assigns it to y by this rule right here. And the rule is 2 over x plus 3. So our 2 over x plus 3 is the rule, and that tells us how to take a domain and assign it to a range. And remember that f of x is just another name for y, so that's how I calculate my y value. So for example, f of negative 2. What does this rule f do to negative 2? Well, it assigns it to a y value based on this rule 2 over x plus 3. So we literally just substitute negative 2 in place of x, right? And that's all the rule is saying. You take whatever x value you've got, you add 3 to it, and you divide 2 by the answer. And so what do I get here? I get 2 over 1, or 2. So we say that f of negative 2 is 2, right? That this rule f takes negative 2, the domain value, and it assigns it to the range value 2. And if you wrote this as an ordered pair, you'd have the ordered pair negative 2, 2. Right? We could go on with this. F of 5 would be 2 over 5 plus 3. Right? When we try to figure out what this rule does to 5, we just substitute the 5 in place of x. Right? And we do what the rule tells us to do. So this is 2 over 8, or 1/4. So f of 5 would be equal to 1/4. Right? This rule f takes 5, the domain value, and it assigns it to the range value 1/4. As an ordered pair, this would be 5 1/4. Right? 5 would be the domain, 1/4 would be the range. Now let's look at the reason why I brought this particular example up is let's look at what this rule does with negative 3. So the rule is f. We've got the rule stated at the top. It's 2 over x plus 3. So how do we figure out what this rule does with negative 3? We substitute negative 3 in for x, and we get 2 over 0. Now don't you dare tell me that 2 over 0 is equal to 0. Right? 2 over 0 is not equal to 0. Remember, you cannot divide by 0. The 2 over 0 is actually an undefined expression. Right? This is a meaningless expression. This is undefined right here. Remember, you cannot divide by 0. Right? There's no way to do that. There's no number you can multiply by 0 and get 2 as the answer. So this is undefined. So what happens? This function does not assign this rule f does not assign negative 3 to a range value. Just like a minute ago when we looked at Bob from our class and we saw that Bob did not own a car, and so the rule 2 we were looking at in the last screen did not assign Bob to a make of car. So what did we do with Bob? We threw him out of the domain. This is exactly what we're doing with negative 3. This rule f does not assign negative 3 to a range, so we throw negative 3 out of the domain. We toss it. And so the domain for this function ends up being everything except negative 3. I'm just going to write that in words right now. We'll look at that a little bit more carefully later, and in college algebra, you'll look at this in much greater detail, certainly. But the domain for F is all reals except x equals -3, right? -3 is the only one where this happens, where you get division by 0, and so you don't get an answer. And so the domain for this particular function is all reals except for -3. And you should start getting the idea right away from this problem that when you have a fraction, right, when the rule is a fraction like this one, 2 over x plus 3, you do not want 0 in the denominator of that fraction. And any x value that makes that denominator equal to 0, you can't use it, right? And that's going to be a big deal for us as we proceed on through algebra. So as you get into college algebra, that's going to come up in several different places where it's going to matter whether, where the domain is equal, or where the denominator is equal to 0. All right, so now let's go back to rule 2, because the reason why I looked at that example is because of this throwing Bob out stuff. So we've thrown Bob out, then we throw everybody who's a non-car owner out of the domain. So all non-car owners are thrown out of domain. And so what are we left with? What we are left with only people who own cars, right? So the question is it a function? That we still haven't answered that. So now what we're left with is just this subset of people, the subset of the domain, of the original domain, where the people actually got assigned to something. They actually own a car. So now the question is, does this satisfy the definition for a function? So let me give you two ordered pairs that I know happen to be in this, because I consider myself as part of the class. I'm part of the domain also, right? And so it says everyone gets assigned to the make of car they own. So I own a Subaru and I own a Toyota. I own two cars. And so look, that's a problem, because if you look at those two ordered pairs right there, how many domain elements do you see in those two ordered pairs? How many x's do you see? Well, those two ordered pairs have the same x value, right? And so it's just one x value, but what happens? You have one x value that gets assigned to two y values. Sometimes you'll see that written out kind of in a chart form, where you'll see the domain value written and then arrows to signify the relationship. And you have Jim would get assigned to Subaru and Jim would get assigned to Toyota. That is something that cannot happen, right? And so we don't, once that happens, once we have a domain that's assigned to two ranges, that kills it right there. It is not a function. So this is not a function. We have at least one, and there's probably others, certainly, but we have at least one domain that gets assigned to multiple ranges, and that is a problem, right? And so we can't do that. And so going back to our definition, a couple screens ago, we wrote underneath our definition that repeated y values were okay. So if you had a set of ordered pairs and they had the same y value, that was okay, not a problem. Well, what else should we add now? That repeated x values, let's see, let's spell this right. Repeated x values are not okay, right? If you have repeated y values, you still have a function, but if you have repeated x values, you do not have a function. You have a relationship, but it is not a function. It doesn't satisfy the definition for a function because you have a domain that gets assigned to multiple ranges. All right, so that kind of covers the definition. So hopefully you're starting to get a little bit better of an idea of what this definition is all about. So now let's look at some examples here and kind of piece together some things about functions. First of all, one way you might see a function written out or rules written out like this is you might use or see what's called an arrow diagram. So with an arrow diagram, you have the domain values listed, you have the corresponding range values listed. So, there might be things, it might be in the list, it might be numbers, it could go all sorts of different ways. It could be letters, whatever. So like maybe we have, this is our domain, A, B, C, D, and E, right? Just the letters, the small letters from A through E. And our range, let's say, are colors. Red, green, purple, orange, yellow, pink, like that. And an arrow diagram will look like this, that the domain value, you draw an arrow from the domain value to the range value that it's assigned to. So like here, A is assigned to purple, B is assigned to red, C is assigned to green, D is assigned to yellow, and E is assigned to purple, like that. And so the question is, does this satisfy the definition for a function, this arrow diagram? And so you have to remember, you have to answer two questions. Does every domain get assigned to something? Yep, every domain has an arrow coming from it. And does every domain get assigned to exactly one thing? Yes. Some of the domains get assigned to the same thing. That doesn't matter, right? Remember, we can also write this out in ordered pair form, right? And so in ordered pair form, you'd have A would be the domain value, and the color it gets assigned to would be the range value. So A gets assigned to purple, B gets assigned to red, and so on, right? You'd list these ordered pairs out. Also remember that since this is a function, we can use function notation, and we might say that f of D, for example, what would f of D be equal to?
Yellow.
F of D would be equal to yellow. All right, D is the domain, and based on this arrow diagram, yellow would be the corresponding range. So f of D would be equal to yellow. F of E would be equal to purple, and so on. Right, and we have a function. We've written it out in function notation. We have an arrow diagram. We could write it out as a set of ordered pairs. We have all these different ways that we can write this out. All right, so that's a good way to picture a function. Let's look at another one. Let's say that the domain now is maybe somewhat more traditional, just the whole numbers from 0 through 5, and this is our range. Let's say it is also the whole numbers from 0 through 5. And this is the way our arrow diagram looks. 0 gets assigned to 1, 1 gets assigned to 0, 2 gets assigned to 3, 3 gets assigned to 3, 3 gets assigned to 4, 4 gets assigned to 5, and 5 gets assigned to 2. So function or not a function in this case, based on this relationship. Function or not a function?
Not a function.
Why? You'd have to be able to answer why, okay?
Three is-
Oh, go ahead.
3 is assigned to 3 and 4.
Right. That's right, Charlotte. And I think, Janessa, you were going to say the same thing. That's right. So why?
Yeah.
The question is why, and what do we have? We have two ordered pairs here. We have 3 gets assigned to 3, and 3 gets assigned to 4. Or as with an arrow, what happened? You had 2 arrows coming out from 3 like that, and that's a problem. That can't happen when you have a function. That's not allowed right there. So the arrows can come together and point to the same thing, right? That's okay. But what you can't have, like in this case, 2 and 3 both get assigned to 3. That's not a problem. Repeated y's are okay. Repeated y's are okay. Repeated x's are a problem, right? Can't have repeated x's. Can't have repeated x's. So not a function. All right, we're good? Everybody's all right? So now, so arrow diagrams is one way you might see a function written out. You might see a function written out simply as a set of ordered pairs. So 1, 6, 8, 10, 11, negative 3, 12, negative 15, 13, 10, like this. And so with this set of ordered pairs, would this be a function or not a function? What would the domain be, first of all? The domain for this would be 1, 8, 11, 12, and 13, and the range would be 6, 10, negative 3, and negative 15. Function or not a function?
Function.
Yeah, function in this case. And so, yeah, definitely this would be a function, right? And in this case, we could say function, and we just simply write no repeated x's, right? All the x's appear just once, and that's really all you have to look at is whether there's any repeated x values here at all. So we could name this function, like we might name it f, and name this set f. And the domain for f, this is the notation we'd use for the domain for f. We'd put a capital D, and we put a subscript on the D, which is the name of the function. So the domain of f would be the set 1, 8, 11, 12, and 13, like that. The range for f would be the set 6, 10, negative 3, negative 15. And we don't write 10 twice. We don't write repeats down like that. Right, and from function notation, what would we have here? We'd have that f of 11, for example. Right, this is saying what does this rule f do with 11, and what does it get assigned to? And it gets assigned to negative 3 because of the ordered pair 11, negative 3. So you have f of 11 is negative 3, and f of 13 is 10, and so on. F of 1 is 6, right, and so on. All right, so that set of ordered pairs represents a function. All right, and this set of ordered pairs all right, what about that set of ordered pairs? Function or not a function?
Function.
Yeah, it's a weird function, isn't it? Sandra said function also. Definitely a function. It's a weird function. It's called a constant function because what happens, every domain gets assigned to the same range. That's not a problem. No big deal. Every domain got assigned to one range. That's okay. Right? There's still no repeated x's. And so that would be a function right there. All right, and so we could name that g, for example. And so what would we have here? The g of 8 is 3, and g of 9 is 3. G of 10 is 3, right? G of all the domains is equal to 3. That's why it's called a constant function. And there are functions that we're going to look at that are going to be constant functions. They're actually sometimes the constant functions an important function, important in applications, believe it or not. All right, let's say we have 2, 1. 3, 4, negative 10, 11, 6, negative 15, 3, 15. Function or not a function?
Not a function.
Yeah, not a function, that's right. This is not a function, and what happens here? We have repeated x's, don't we? That's a problem. And where do we have repeated x's here? Well, we get that 3 was taken to 4, and 3 was taken to 15. So 3 is repeated there. That is a problem. We have one domain that gets taken to 2 different ranges. That can't happen. On an arrow diagram, it would look like this. And that's a problem. All right, so this is not a function on this one. I will ask you this. I'll give you, on the next test, I'll give you a set of ordered pairs, and I'll simply ask you, does it represent a function or not? And, you know, if you know the basic idea that repeated x's are a problem, then those are easy questions, okay? All right, so we're doing good. We're doing good. So now the problem with what I've just written out, the last couple of examples, you know, the arrow diagrams that we started with on this screen, the arrow diagram here, and then the sets of ordered pairs we've looked at, is that these all have finite domains and ranges. Very, very, we could count how many elements were actually in the sets. In algebra, we frequently look at functions. In fact, most of the time we're going to look at functions where the domains and ranges are infinite. And because they're infinite, there's too many values to list them. So just listing a set of ordered pairs would be a problem, right? Because there's too many of them to list out. So many, in fact, most functions that we're going to look at as algebra students and college algebra students, many or most functions have infinite domains and ranges. And the question, or not the question, but the point is too many to list. And so we have to come up with other ways of expressing functions like this rather than just listing out the domains and ranges or listing out the ordered pairs. And so we have that equations and graphs are good ways to show infinite domains and ranges. And so before we leave today, I want to look at both of those a little bit and talk about equations and graphs and talk about how you might think about whether they're functions or not. So let's look at a graph right here. And so I'm going to make up a graph. And so this graph is simply a set of ordered pairs. Let's see, let's go down like that. And here we have a graph right here. Right, it starts here at the point -3, -1. Then there's a line segment that goes up to -1, 1. And then over to 3, -2. And then up finally to 5, 2. Now, how many ordered pairs are on this graph? That's my first question. I'd be curious to say, and before anybody answers, I want everybody just to pause for a second and think about this. And how many ordered pairs are on this graph?
Infinite.
Charlotte, very good. That's usually not the answer I get right away. But the answer is infinite. So the question is, how many ordered pairs are on this graph? And the most common answer is 4, because that's how many I actually plotted there. But remember that when I draw those line segments, that every point on that line segment is a ordered pair that's part of this graph. And points have no width, no height, no length. There's no dimension to a point at all. It's just a precise location. And so there's an infinite number of points on this line segment. Even though it stops in both directions, it doesn't matter. There's no arrows there, nothing like that. This is definitely an infinite set of ordered pairs. So how many ordered pairs are on this graph? The question, and it's an infinite set right here. Now the next question is this a function or not a function? So that's the next question, is function or not a function? And so the question here, remember that question, a function or not a function, really is could be stated like this. It could be stated as, does it have repeated x's or no repeated x's? So repeated x's, question mark, or no repeated x's, question mark, right? That's what you're actually asking. All right, so let's see if we can figure out by just looking at this graph whether it has repeated x values or not. So let's look at an x value that's part of the domain for this function. So an x value that's part of the domain for this function is the x value 2. There's x equals 2. That's where it lives on the x-axis. And remember, on the x-axis, that's where the domains live, is on the x-axis. Right, so the domain's there, and the ranges live on the y-axis. That's their home. All right, so there's my domain value of 2. And so then how does this rule that's drawn out by this graph, that's expressed by this graph, what does it assign 2 to? Well, all you do is you take the x value 2 and you go down to the graph. I'm going to put this in green right here. Right, goes down in the graph right there, and that point is where 2 is how 2 gets assigned, right? And what does this graph do? It assigns 2 to the y value -1, like I've got right there. All right, so what about, and so how many y values did 2 get assigned to? It just got assigned to 1, right? Notice if you look up the graph, you don't see the graph anywhere. And if you look down, you don't see the graph anywhere else. You do see it at that one point at -1. Okay, if you pick the x value 5, right here, right, that's where the domain value 5 lives. And what is the range value that corresponds to 5? Well, if we look up, we see this point right here at 5, 2. But we don't hit the graph anywhere else. Everywhere else on this line is x equals 5, right? And that nowhere else on that graph would you have x equals 5. And so 5 gets assigned to 2 by this graph. It doesn't get assigned to anything else. And so no repeated x value there. Right? We could keep on going like this. So let's do something kind of different. Let's say we've got the x value -2.6. -2.6 is approximately right here. There's -2.6. And so -2.6, we see gets assigned to that point, whatever that y value is, maybe approximately -1/2 right there. And does -2.6 get assigned to any other y value? Well, there's x equals -2.6 on that line right there, and no. That's the only one we get. So you get -2.6 right there and about approximately -1/2 right there. We'll just say -1/2 or -0.5 since I was using a decimal on the other one. So let's say -0.5. The idea is that when you look at a vertical line, when you pick an x value that's part of the domain, if you look along a vertical line that goes through that x value, how many places does that vertical line intersect the graph? And if it just intersects once, then you don't have any repeated x's, right? And notice in this case, this graph doesn't have any repeated x's at all. And so this would be, this graph represents a function. So that, and what we're using here, this idea of these vertical lines is called the vertical line test. And I'm going to write that down, the vertical line test. And what are we seeing here? That the vertical line test says that all vertical lines intersect only once. So all vertical lines only intersect the graph once. And so since they only intersect the graph once, right, no repeated x's. At all. And so this graph does represent a function, right? This graph is a function. Now also notice that, as I was picking these x values, I had to be concerned about what values were in the domain and what values were not in the domain. And so I was careful to pick ones that were in the domain and not pick ones that were not in the domain. But we need to explore that a little bit more carefully. So I do want to draw this graph again, the same graph. So now we've established that this graph is a function. The next thing I want to do is I want to look at whether this, or what the domain and the range are for this graph, right? And so let's see, we have -3, -1, -1, 1, that line segment right there. And then we have 3, -2 right here, like so. And then we have 5, 2 right there. All right, so now, so this is a function, and I'm going to write passes the vertical line test, and I abbreviate the vertical line test just VLT, vertical line test. So now the question is, what's the domain for this function? Right, we'll name this function f, and so what's the domain? Well, the way I want you to visualize the domain on this is that picture yourself walking on the x-axis. Right, there you are walking on the x-axis, because you're talking about domains. And you're walking from the left to the right. You always walk left to right. And remember, the x-axis is infinitely far, so you start infinitely far to the left, and you're walking towards us, towards the y-axis, and you keep on walking infinitely far to the right. And as you're walking, you look up, and you look down. Whoops. And the question is, as you walk from left to right, when you look up or down, do you see the graph? If you see the graph, vertically up or down, then that x value that you're standing on is part of the domain. So what happens here? I start seeing the graph at -3, right? At x equals -3 right here. And then I continue to see the graph as I walk along, continue to see it, right? And we look vertically until we get to what value? All the way over here at x equals 5 right here. And so the domain, you could write in words all x's from -3 to 5. I don't like the way that sounds at all, and that's not the way we're going to write it, but that's one way you could write it. What we do in algebra is we use what is called interval notation to write this out. So the interval notation for this set from -3 to 5 is what we do is we put the -3 down, which is the left edge of the domain, and then we put the 5 down, which is the right edge of the domain, and then we put brackets to tell somebody that we include -3 and 5. And what that interval notation tells us, it's every domain from -3 to 5. Every x value from starting at -3 and going to 5. The brackets mean that the -3 and the 5 are actually part of the set. Now we'll look at one in a minute where that's not part of the set, but that's what we're talking about so far. All right, so let's talk about the range now for f. So the range for f, we'll do this maybe in a different color, maybe in blue here. So with the range, what you're doing, hold on real quick here. All right, so what we're doing with the range, it's like we are on the y-axis, and we're actually climbing up the y-axis. So there's my picture. I have very good art skills, and so that's very well done, I think. Just being sarcastic there. So as we're climbing up the y-axis, and we always climb from bottom to top, the question is, do we see the graph as we look to the left and to the right? So as you're climbing up the y-axis, you're looking left and right. And if you see the graph, all that means is you have a y value. And remember, if you have repeated y values, that's okay. That's not a problem. So as this person's climbing up the y-axis, what happens here? They start seeing the graph at -2 right there. And then as they move up, sometimes they see the graph twice. Sometimes they actually see the graph 3 times. That's okay. Repeated y's are okay. And as they climb up the y-axis, when's the last time they see the graph? The last time they see it is at y equals 2. So the first time they see it is at y equals -2, and the last time they see it is at y equals 2. And so the domain, I'm sorry, not the domain, the range for f is all y's from -2 to 2. And the way we write that in interval notation is we put a bracket with a -2 and then a +2, and then we close the brackets like that. And so that's that's the way we write the domain and the range. So this graph is a function. It passes the vertical line test. And then we walked along the x-axis to look at the domain. We climbed up the y-axis to look at the range. All right. So that's a good start right there with that problem. Even though we've kind of made a mess of that graph, it's a good start. We won't make that much of a mess the next time. All right, so let's look at our next graph. Our next graph is going to look like this one right here. We have that line segment, and then we have this line segment like this. All right, so let's see, that point right there is at 2, 0. This point right here is at 5, -2, and this point's at 5, 3. So first of all, with this graph, again, remember, there's an infinite number of ordered pairs on this graph. But the question is this a function? That's our first question. And this is what I'll ask you on the next test. I'll give you a graph. First thing I'll say is it a function? And I'll ask you to tell me why it is or why it's not. And in this case, what's true? This is not a function, is it? Because what can I do? I can draw a vertical line that intersects this graph twice. And because they have a vertical line that intersects twice, I can draw multiple lines like that. Vertical line intersects twice. That means I have repeated x's. It means the graph fails the vertical line test. So it will write fails the vertical line test. And if I ask you to tell me whether this is a function or not in the test, and I ask you to tell me why, that's how you can respond to why. As you just say, it fails the vertical line test, right? It means it has repeated x's. So you just say fails the vertical line test. Now you can still talk about the domain and the range for this graph, and that is good practice for us because that I know is a hard skill for students sometimes. So let's talk about the domain and the range for this graph. Even though it's not a function, it still has a domain and a range. So with the domain, remember what you're doing is you're walking along the x-axis, right? Walking along the x-axis. And you're always going from left to right like this. And so the question is where, and then you're looking up and down. Remember, you're looking vertically as you walk from left to right. And the question is, as you walk from left to right and you're looking vertically up and down, where do you see the graph? And you start seeing it at 2, at x equals 2, and you stop seeing it at x equals 5. And so the domain for this graph in interval notation would be bracket 2 to 5, and close the brackets like that. It means every x value from 2 to 5. Okay? And then on the range, let's see, so the range, we are talking about climbing up the y-axis. All right, so there I am climbing up the y-axis. And as I move up the y-axis, what am I doing? I'm looking left and right. You're always looking left and right as you climb up the y-axis. And you're always going from bottom to top. And so where do you first see the graph? You first see it right here at y equals -2. And then you last see it here at y equals 3 as you climb up the y-axis like that. And so the range here is going to be everything from -2 to 3 like that. All right, and so that we've written out the range on the function. Okay, so we're doing good. We're doing good. I want to look at definitely want to look at a couple of more situations here, a couple things to finish with, and we've gotten a lot covered today. We have a lot of explanation to do, definitely. So let's just simply look at a graph. Let's see, this one is kind of the upper half of a parabola, or not the upper half, but the upper part of a parabola, we'll say. So it looks like this. But now notice that those open circles right there at the ends of the graph imply that graph, don't imply, they say that those points are not actually part of the graph. So this point here at -2, 1 is really not part of the graph. And this point right here at 2, 1, and actually let me change that. Let me make that one a solid dot. We'll put one of them as an open circle and one of them as a solid dot. That way you'll see the difference. All right, so first of all, function or not a function? That's our first question. Function, question mark. And in this case, the graph passes the vertical line test. Every vertical line intersects the graph only once, and so this graph passes the vertical line test, and so the answer here is yes, it is a function. The next question is, what is the domain and the range? So let's call this function g right here. So what's the domain of g? Okay, so here I am walking along the x-axis, right? Here I am walking along the x-axis. And as I walk along the x-axis, I'm looking vertically. Right? If I can see the graph vertically above me or below me, then the x value is part of the domain. Now notice that at x equals -2, there's that open circle right there. And so that is not, x equals -2 is not part of the domain there because of that open circle. But then anything past -2, these x values all are part of the domain, right? You can see the graph there and see the graph there, right? And then you can see the graph here at x equals 2. So what's going on with the domain in this case? Everything between -2 and 2, I can see the graph, -2 and 2 like this. At 2, I can see the graph because of that closed circle, so I put a bracket there. But at -2, there's that open circle, and so that we put a parenthesis around, and that parenthesis implies that x value is not part of the domain. -2 is not part of the domain there. Okay? And then the range on G, we do the same thing now, but we're looking at a horizontal line, right? So we are climbing up the y-axis, and we're looking left and right. So we're climbing up the y-axis, we're looking left and right. And so the question here is, do I see the graph here at 1? At y equals 1? And I do, don't I? Because one of those places, it's a solid dot. One of them is an open circle. And so I do see it at least once at y equals 1. And then I see it all the way up to y equals 4 right here. And so the range on G is going to be from 1 to 4. And then I put brackets around both the 1 and the 4 like that. Because both at y equals 1 and y equals 4, I can see the graph. Also, let's talk a little bit about function notation here. So what would g of 2 be equal to? What do? You look at the x value 2, which is right here, right? And you see the point would be 1 at the point 2, 1. So g of 2 is equal to 1. G of 0 would be equal to, that's when x is 0. And when x is 0, which is at the origin, you look up and you see the graph is at 4. So g of 0 is equal to 4. Right? So I want you to start being able to read function notation off of a graph also. All right. And then, so we're doing good on graphs. That's about as complicated as we're going to get on graphs today, for sure. And then the last thing I want to do is talk just very briefly, so I'm about 3 minutes from being finished here, by looking at equations. So we've been looking at graphs, and now let's look at equations like f of x equals 2x plus 3. Now, you have y equals 2x plus 3 is another way to write that same equation. Remember, f of x and y mean the same thing. And this is a function because every every time you use an x value, you get just one y value back. You can tell by the way the equation is written. I'm not going to worry about the domain and the range right now for this equation. All I want to do is look at the function notation here. And I want to make sure that when you leave our recorded lecture today, that you have at least a little bit of an idea of how function notation would work from an equation. All right, so, and we've actually talked about this a little bit already, but let's look at it again. So, for example, f of 3, right? F is the name of the rule that we're using, and 2x plus 3 is actually the rule. F is the name of the rule, 2x plus 3 is actually the rule. So what do? You substitute 3 in for x. So f of 3 would be 6 plus 3, or 9, right? F of 3 is equal to 9. The ordered pair is the point 3, 9 right there. F of -5, the domain value is -5 here. And so this rule would take -5, we would put it into for x, and this rule would take -5 and assign it to -7. So f of -5 is -7. You have -5, -7 is the ordered pair here. That's that tells us that -5 gets assigned to -7, like that. F of t, okay, that sometimes will throw students off, but that t is just a domain value. And so what would this function do with that domain value t? Well, it would do the same thing that it did with any of the other domain values. It would multiply it by 2 and then add 3. And so you get 2t plus 3. You couldn't do anything with that, but that's what it would be assigned to. So technically, the ordered pair would be, it looks weird, but it's true, the domain value would be 2, and the range value would be 2t plus 3, like that. F of a plus b, and you're going to have to be able to evaluate function notation like this that's going to come up in applications, believe it or not. So the domain value is a plus b. And what do? How do you find what this rule assigns a plus b to? You put a plus b in place of x, just like we did with t, and just like we did with -5, and just like we did with 3. And then you could just multiply this out. You get 2a plus 2b plus 3. So the domain value here would be a plus b, and the range value would be 2a plus 2b plus 3. Right, that's what this function, f of x equals 2x plus 3, does with the domain value a plus b. And I want you to see in every case, what did I do? I took our function 2x plus 3, and all I'm doing is dropping these x values in place of these domain values in place of x. Right? The domain values are just different for each one of these statements, but I'm doing the exact same thing for every problem right there. Right? I'm taking that function and I'm substituting a domain value in for x there. Okay, so that's my opening lecture on functions. That's what we're gonna. That gets us a good start. Does anybody have anything that they really need to ask here as we move on here? Anything?
I'm good.
All right. So okay, then no questions. So the homework from the textbook. Remember that this is from the intermediate textbook. So the intermediate text. And the page, this is section 3.5, and that, or section 3.5, page 325. And this would be problems 283 through, now it sounds like a lot of problems, and I'm not necessarily expecting that you do all of these by any means, but definitely by any means, but any of these odds would be great practice, 283 through 327. So the more of those odds you can get done, the better off you are as we proceed on. And we will talk more about functions and graphs of functions next time. So if no one has any questions, please don't hesitate to come by my online office. I have online office hours again for your class on Sunday from 7:30 to 9 o'clock, and Monday from 8 to 9 o'clock. So don't hesitate to come by. Remember, we do have lecture next Tuesday, even though it's Thanksgiving week. So don't hesitate, or please try to come by for a live lecture if you can. Have a great week. Get started on the Exam 3 review. Keep up with your WebAssign homework. Have a great day. Take care.
You have a good one.
Thank you, Charlotte. Good luck. Good work
Thank
on
you,
the
Amy.
factoring contest.
Thank you.